Welcome to ES 310 Lesson 37. Today will be a brief review of the material we've covered thus far in this class. As a reminder, we started in Hibbler's Dynamics textbook in Chapter 12 and have now completed Chapter 22. By way of an overview for this class so far, we've looked at kinematics and kinetics. And we've looked at kinematics and kinetics for particles, rigid bodies, and in 3D. So let's look at each of these combinations briefly. So in kinematics, we're looking at the motion itself, not worrying about the forces that generated it. And so with particles, we were interested in variables, position variables like x and y, velocity variables, vx, vy, and acceleration variables, ax, ay. Or we looked at those same variables in either the normal tangential coordinate systems or the radial theta coordinate systems or the polar coordinate systems. When we went to rigid bodies, we allowed things to rotate, and so we added the variables theta, which is the rotational position variable, omega, which is the rotational velocity, and alpha, which is the rotational acceleration. In 3D, we added a third dimension, so we added the z variable for position, velocity, and acceleration. So then once we had looked at the kinematics for each of these situations, we moved on to the kinetics for these situations. And in the kinetics, we're interested in forces and how they influence the kinematic variables. So we first looked at Newton's second law. And Newton's second law said that the force was equal to mass times the acceleration. So the variables we're interested in these cases are forces, masses, and accelerations. And those forces could be for particles in the x and the y directions. In 3D, we add the force in the z and the acceleration in the z. For rigid bodies, things could rotate. So we had sum of moments was equal to I alpha. And so we have added moments of inertia, and rotational acceleration. In 3D, for rotation in 3D, we also had all of the other i's, so IZZ, IXY, IXZ, and IYZ. So we had a matrix of 6 different moments of inertia. So we also looked at kinetics through work energy. In work energy, we're looking at the forces working over distances. So we have forces and masses as before. Now instead of accelerations, we have positions and velocities. So the energy is often related to velocities. Works were forces over distances. We had them in the x and the y direction. In 3D, we had them in the z direction as well. When we added rotation, we had rotational work and rotational energy, and so we added the moment of inertia, the theta, which is the rotational distance, and omega, rotational velocity. The final method we looked at for kinetics was impulse momentum, and impulses are forces acting over times. So we have forces and times, masses and velocities. Rotational, we add the rotational force, which was the moment, rotational mass, which is the moment of inertia, and rotational velocities. And in 3D, we add the z dimension and all of the various i's. So let's go through each of these topics, and what I've done is combined all of the key equations that we used onto a single slide. So these are crowded slides, but it's a good review of the class. So in kinematics, we started by looking at translation. In translation, we defined the velocity as the time derivative of the position, the acceleration is the time derivative of the velocity, and we had this combined equation, a ds is equal to v dv. If the acceleration is constant, we could write out these 3 equations. And these 3 equations, when written in 2 dimensions, so for the x and the y directions, give us our projectile motion equations, which we used quite a bit. In the curvilinear coordinate system, we had normal tangential coordinates. So the tangential acceleration was the time derivative of the velocity, and the normal acceleration was v squared over rho, where rho is the radius of curvature of the motion. We could also describe curvilinear motion in the r theta coordinate system. In that case, the velocity is the time derivative of the radius, and the v theta is equal to r theta dot. The acceleration is given as expressions in terms of r and theta as well. And so if you think back to using r theta coordinates, that's where we found r and theta, r dot, theta dot, and r dot, double dot, and theta double dot, and plugged all of those various expressions into our acceleration definitions. We looked at absolute motion at one point. So that was using geometry to relate the various positions, and then differentiating those relationships to find velocities. That was also where we looked at pulley systems. Then we looked at relative motion. So if we know the position of point B and the position of point A, we can find the position of point B relative to point A, or as measured from point A. We can do the same thing for velocities and accelerations. So this was where, if you're in a moving car, how fast does the other car seem to be moving? Those types of questions. Then we added rotation when we moved on to rigid bodies. And in rotation, we have the same equations, but written in the rotational variables. So omega is equal to time derivative of theta, alpha is the time derivative of omega, and we have alpha d theta is equal to omega d omega. For constant angular acceleration, we have similar equations written in terms of the angular variables. And then in the nt coordinates, we have that the tangential velocity is equal to omega times r, and the tangential acceleration is equal to alpha times r, and the normal acceleration is omega squared times r. Then we have our similar relative motion around a translating axis, for example. So we have the axis is moving and the body is spinning around that axis. And so our definitions were the velocity of point B is equal to the velocity of point A plus omega crossed with the position of B measured from A. And we have the similar equation for acceleration. Acceleration of B is equal to the acceleration of A plus alpha crossed with r, the position of B relative to A, minus omega squared r of B from A. Remember, if we could find an instantaneous center of zero velocity, these were reduced because these terms tended to drop out. If we have rotating axes, then we had this capital omega, which was the angular velocity of the rotating axis. And we had the expression for the acceleration of B as described by rotating axes as well. And this was just a matter of defining all of these terms and plugging them in. There was a lot of cross products in this, so make sure you remember how to take a cross product of vectors. In kinetics, we used these definitions that we had described in kinematics to start looking at the effects of forces on things. And so, Newton's second laws, we used force equal to mass times acceleration. So we had that in the x and the y direction, we had that in the normal tangential directions or in the r theta directions. There's not really anything new here except for the expression force is equal to mass times acceleration. The accelerations were given on the previous slide as part of the kinematic discussion. Since we're dealing with forces, some of those forces often come from springs. So you need to remember that the force due to the spring is equal to k times the stretch in the spring, or the compression of the spring, which is typically written as a length minus the original length. We also dealt with forces from friction, and friction is given by the coefficient of friction times the normal force, and you can have static friction or kinetic friction depending on whether the object is stationary or moving. When we looked at rigid bodies, we added in the ability to rotate, so we needed moments of inertia. We found moments of inertia either from the tables, from the integral expression, or from a radius of gyration definition. This was the parallel axis theorem that we needed to use a lot when we were using tables. And then in rotation, if we have a fixed axis, it makes sense to use normal tangential coordinate systems. So we've got the sum of the forces in the normal is equal to the mass times the acceleration of the center of gravity. So we now care what point on the object we're dealing with. So we're dealing with the center of gravity in the normal direction, which is m omega squared rg. And then we have a force in the tangential direction is equal to mass times the acceleration of the center of gravity in the tangential direction, which is mass times alpha times r. We also have rotation around the center of mass, which is ig alpha, or we can find rotation around that fixed axis, that fixed point, which is io alpha. In general motion, we fall back to the x and y coordinate systems, which are more generic, and we've got the forces in the x is equal to mass times acceleration in the x, forces in the y, mass times acceleration of force in the y. And then we have moments around point G, which is our center of mass, or moments around a fixed point, which is often an instantaneous center of zero velocity, or moments around a random point in which we use these fictional kinetic moments, which is r crossed with mass times acceleration. And so another way of thinking of these kinetic moments would be I around P, where you use the parallel axis theorem times alpha. We also looked at kinetics through the work energy method. So the principle of work energy states that the kinetic energy of an object plus the work done on that object is equal to the final kinetic energy of the object. So to find kinetic energy in a linear sense, so when it's translating, it's 1/2 mv squared. When it's rotating, it's 1/2 I omega squared. So the combination is true for rigid bodies. For particles, you only need this first term. We can also write the kinetic energy is 1/2 IC omega squared. So that would be a point. It's an instantaneous center of zero velocity. So that's a point that isn't moving. So this first term would go to zero. Or similarly, 1/2 IO omega squared. IO is the standard definition of a fixed point. The work part of this is given by U. And if it's a constant force, arbitrary force, it's equal to that constant force times the path that is parallel with that force, or the cosine theta, where theta is the angle between the force and the path. For gravity, which is a common force that does work, we have a work times the change in y, because gravity always works in the y. The negative sign indicates that the gravity is pulling down, whereas typically a position is measured upwards. So if we change, so if our force and our distance are in the same direction, our work is positive, whereas if our force and our distance are in opposite directions, our work is negative. So gravity is typically negative if up is a positive direction. The work done by a spring is 1/2 K times S2 squared minus S1 squared, where S2 is the final position and S1 is the initial position. If we have a non-constant force, we need to use an integral. So it's the integral of F dotted with ds, or the integral of F times the component of S, the path that is parallel to F, which is given by this cosine of theta. If we are dealing with rotation and we have moments applied to our system, then the work due to a moment is the moment times the change in angular displacement. If we have a situation where there's no friction, then all of our forces are conservative, and instead of using the principle of work energy, we can use the conservation of energy. Conservation of energy says the kinetic energy plus the potential energy is a constant. So at any 2 points, T plus V, are equal. The potential energy is given for gravity as W times yg again, similar to the work done by gravity, and is given for a spring as 1/2 ks squared. You can pick your reference points for both gravity and springs. So pick them as convenient points to simplify this equation. And remember, if you pick a datum point and you go below that datum point, you're going to have negative potential energy. You go above that datum point, you're going to have positive potential energy due to gravity. The kinetic energy in the conservation of energy is again given by the same kinetic energy equations that we just discussed. The final method we used in looking at kinetics was the impulse momentum method. So here we define momentum, linear momentum, as the mass times the velocity. Since velocity is a vector, momentum is also a vector, and so we look in the x direction, the y direction, and if we're in 3D, the z direction as well. That momentum plus the impulse, which is the integral of the force times the time over which that force acts, and you do that for all of the forces in the system, is equal to the final momentum in that direction. Rotationally, we also have rotational impulse momentum, which gives us this I omega, which is rotational momentum, plus the moment times dt integrals, which is the rotational impulse, is equal to the final rotational momentum. And we can use either the center of gravity or an instantaneous center of zero velocity in these equations. Conservation of momentum applies when we have non-impulsive forces, which means the forces in our systems don't cause impulses. Either they're very small compared to forces that are causing impulses, they're very short duration. If conservation of momentum is true, then we have the sum of the momentums in a system before some sort of impact usually happens is equal to the sum of the momentums in the system afterwards. And similarly for rotation, we have the sum of the angular momentums is equal to the sum of the angular momentums afterwards. For a general point, we can write the angular momentum as the angular momentum of that point using IP plus the y direction times the linear x momentum plus the x direction times the linear y momentum. And so this should remind you of the fictional moments we just looked at. If we don't know the final velocity of either particle in our system, A or B, but we do know a coefficient of restitution, which is a measure of how much energy is lost when they hit each other, then we can find those two using this coefficient of restitution definition in collaboration with the linear or the rotational momentums. The last topic in the class was vibrations. If you remember, we started by looking at undamped vibrations, but that is just a special case of general vibrations. So this slide shows things in terms of general vibrations. So in terms of general vibrations, the standard form of the equation is this one, where there's a 1 in front of the double dot term. The coefficient of the single dotted term is 2 zeta omega n, and the coefficient of the undotted term is omega n squared. And so we can use these coefficients to find the natural frequency, which is omega n, and zeta, which is the damping coefficient. So in the case of undamped motion, so vibrations that will never die out because there's no friction or any other losses, zeta is equal to 0. And the general form of the solution for this motion is a sine omega nt plus b cosine omega nt. You can solve for a and b using the initial conditions, which sometimes will require you to take the time derivative of x if you're given information about the velocity at time equal to 0. For damped motion, there are three possibilities. We have overdamped motion, which means there's no vibrations and the motion simply decays to a given level. And that solution is given as a e to the lambda t plus b e to the lambda 2t. The lambdas can be found based on omega n and zeta, and a and b once again can be found through initial conditions. The critically damped case is the situation in which zeta is equal to 1. In that case, x is equal to a plus bt e to the negative omega nt, and a and b can once again be found from initial conditions. Finally, the underdamped case, which is the most common, has zeta less than 1. So this is a situation where you have vibrations that eventually die out to 0. The solution here is x is equal to a e to the negative zeta omega nt sine of omega dt. Omega d is the damped natural frequency, which is a function of omega n and zeta. Once again, a and b can be found from the initial conditions. You can also write this in the form of d e to the negative zeta omega nt sine omega dt plus phi. And d and phi can be found from the initial conditions. In the case of forced vibrations, we have a forcing function on the right-hand side. So the standard form once again has 1 in front of the double dotted term, 2 zeta omega n in front of the single dotted term, and omega n squared in front of the x term. So we can solve for omega n and zeta. And the coefficient in front of the forcing function, which could be a sine or a cosine, is d naught. And the frequency of the forcing function is omega naught. Knowing then those four things, we can find the solution to this system, which is x equals to this first part, which is the free response, which can be written as c sine with the phi, or a and b, plus x prime sine omega nt phi prime. And x prime is given as a function of the four variables we can find from our standard equation, d naught, omega n, omega naught, and zeta. And phi can also be found as a function of those four variables. A comment here, this free response is for the undamped case. If zeta is less than 1, equal to 1, or 1, this part of the response is whichever one of these is appropriate for that situation. We can also have a magnification factor when we have forced vibration, which is due to a relationship between the driving frequency omega naught and the natural frequency omega n. In the case of no damping, this magnification factor can go to infinity if omega naught is equal to omega n. In the case where there is damping, these can still be very large, but will never go to infinity. So to find the magnification factor, which is the ratio of the output amplitude to the input amplitude, we use this expression, which once again is the function of omega naught, omega n, and zeta.